Okay, here we go. Okay, I'm going to be doing this circuit question. Okay, so A. Find the reading of each ammeter and voltmeter after S is closed. Just after S is closed, right? So that's at almost T is equal to 0, basically, which is basically just T at the very beginning. And very quickly after the switch is closed. Let's find all of the A's and all of the B's. So I. So let's start with I2, right? Just because I2 is interesting, that's one over here. So we're going to start with that. I2 is going to be equal to 0. Why? Because the current has just been turned on, and the inductor is therefore creating an induced current that is in the opposite direction of the current that's flowing into the circuit. And basically what's happening is this is going to read 0, and this wire, it's going to be as though it has a break in it, and therefore no current is going through it. That's what it's going to be equivalent to. And therefore the only circuit that we're going to have to worry about is the only part of the circuit is this part of the circuit and this part of the circuit. So let's just draw that. We have this 50 ohms, then we have this capacitor, and then we have this other 50 ohms, and then we have the EMF, right? EMF is 40, this is 50, this is also 50, here we have this capacitor. The capacitor is actually going to act as though it's a regular wire, because there is no Q/charge that is accumulated on the capacitor yet, because the switch was just closed like right now. Therefore this is going to act as though it's a wire. And then so the equivalent resistance of this new circuit is just going to be, let's say that, so we have our 40 volts, and then our equivalent resistance is 100, because since these resistors are in series, you just add them to find the equivalent resistance. So we have, this is our new equivalent circuit. And so, okay, and now we need to measure the current going through this circuit in order to find the current going through here and here, and to figure out what I1 and I3 are equal to. Right, here's I1, here's I3. So we have the voltage is equal to 40, and the voltage and the R is equal to 100. Voltage divided by the voltage divided by the resistance is going to be equal to the current, and this is equal to 0.4, and therefore we have 0.4A, which is also going to be over here 0.4A and here 0.4A, because these are all in series, and current in series is the same for all of the resistors and for the total resistance, the total equivalent resistance. And now we need to find the V's. Let's start with V4, right? It seems random, but it's actually really relevant which one we start with for me in the way that I reasoned this out. So V4 is going to be equal to, okay, so we have, the reason I want to start with V4 and also V1 is because we have the resistances and we have the currents for both of these voltages, and therefore it'll be really easy to figure out, sorry, I hope I said the right thing. We have the currents and we have the resistances, yeah, for each of these voltages, so it's easier to figure out the voltage. So V4 is going to be equal to 50, that's the resistance, times 0.4, which is the current, and that is 20 volts. And then this is also happens to be 50 and 0.4, so this is also equal to 20 volts. Okay, now V for this resistor over here, V3, is going to be equal to 0, because there's no current flowing through here, because it's as though this wire is cut in half, or like has a break in it or something, and there's no current going down this way. So V3 is equal to 0. Now V2 is interesting because V2 is on the inductor. The inductor does have a current, and by definition it has a volt. I mean, sorry, it doesn't have a current. It does, whatever, but I'm saying the inductor does have a voltage because by definition the inductor is going to have an induced voltage, right? So what is that voltage? Well, since this line of the circuit and this line of the circuit are parallel to each other, the voltage is going to be equal to the voltage over here, right? Because two parallel circuits, like circuit parts, are going to have the same voltage. So we know the voltage over here is 20 because of this resistor, and so therefore the voltage here is also going to be 20. So 20 volts, and the capacitor voltage is going to obviously be 0, V5, because the capacitor is not yet charged, therefore there's no current, therefore there's no voltage. So the equivalent voltage so the voltage through this whole line is just equal to the voltage for this 50 ohm resistor, which is 20, therefore this whole line will have to also have 20 to 20 volts of voltage because these are parallel. Okay, next we need t approaches infinity. So that's a long time after the switch is closed. So yeah, let's start with I3. So that's A3. Sorry, I3, A3, I2, A2, I1, A1. Same thing. So A3 slash I3. Here, the switch has been closed for a very long time. Therefore, the capacitor is fully charged, and no current is going to pass through the capacitor, right? Last time, I hope I said this properly when I was discussing the last part, but last time the capacitor acted like a general wire, right? Because there was no charge on it, and it just acted as though it was a normal wire, and it was therefore negligible in our calculations. Now the capacitor is fully charged, which means that no current is going to pass through this section of the circuit, right? Because, yeah, so the inductor is just going to act like a wire because now there's no change in I through that point. So since there's no change in I with time any longer, the inductance will not be it. It's the inductance, the induced voltage will be 0, and therefore I will also be 0, and just everything will be, so, sorry, not, I won't be 0, I'm sorry. The inductor basically will just act as though it's a wire. So before we had the inductor acting as though the circuit did not exist and the capacitor acting like a wire. Now we have the inductor acting like a wire and the capacitor making this part of the circuit look like it doesn't exist really. Okay, so I3 is going to be equal to 0 because, as we just said, the capacitor is now fully charged. Okay, now we want I2 and I1. So let's draw our equivalent circuit. So it's going to be, this is a resistant that is still important, resistor, and we have this 100 ohm resistor, right? And I didn't draw the inductor because the inductor is as though it's a regular wire now. So because it's a very long time after the circuit is closed, and therefore I is constant. So then we've got our real equivalent resistance is going to be equal to 150 ohms, right? And we still have a 40 voltage EMF. So in order to figure out the current here, we know that the voltage over the equivalent resistance is equal to the current, and that is going to be 0.267, and that's also going to be the current here and the current here, because these are all in series, and the currents in series are all the same. So that's what we have with that. Then we need the voltages. So starting with voltage 1, right, and 3. That's just what we just calculated. So we've calculated A2, and we want V3, which is connected in the same current. This has this current and this voltage. And we want V1, which is over here, which is also over here. And, sorry, V1 over here, which is 50 ohms, V1, okay. So in order to figure this out, we have the currents for each one of these is 0.267, and we need to multiply that by the resistance. So the resistance at V1 is 50, the resistance at V3 is 100, so we get 13.3 volts over here and 26.7 volts over here, right? And we now need to do the V of the capacitor. Well, first let's do the V over here. So V4 is going to be equal to what? So it's going to be equal to 0. Why? Because there's no current passing through that section. As we just discussed, the capacitor now fully charged, no current on this side, therefore no voltage over here. Since there's no voltage over here, we need now find voltage over here, V5, over the capacitor. And we know that the voltage here in total equals 26.7, right? Because this V3 is going to have 26.7 volts, right? And these are parallel circuits, like circuit parts, therefore this branch also has to have 26.7 volts. Since they are parallel, they will both be 26.7. Now we have to just find the V during the V over the inductor, which is V2, and that's going to be 0, because this is just going to act like a regular piece of wire now. Okay, so those are all of the values that we need in terms of A and B. Now do the rest of the question. Okay, so C, find the maximum energy stored on the capacitor and when does this occur? So max energy in the capacitor. Max